This is our really beginning of looking at the science of oceanography, or marine science as we call it. And we're going to start at the beginning today, not just the beginning of our course, but also the beginning of the universe. Okay? So remember that, very interestingly, our little planet, which is largely covered by water, by the way, which is the main subject of what we're going to be looking at, is almost a third as long as old as the entire universe is. The astronomers tell us that the Big Bang occurred about 13.5 billion years ago. Okay, about 10 billion years ago, our Milky Way galaxy, of which we are a part, formed, and about 5 billion years ago, our solar system formed. The Earth, as a recognizable planet, we can date back to about 4.5 billion years. We think it wasn't very long after the formation of the Earth that water began to accumulate, and we began to have what today we would call oceans. And it wasn't long after that that life began to develop, more than 3 billion years ago. And one of the things we'll be dealing with later on in the course is, of course, that life in the ocean, a very important part of our course. But for now, I want to go back in time a little bit and look at the formation of the Earth. If we assume now that we have this galaxy, the Milky Way, and remember, you might say that's our home galaxy, in the universe. And you look out at, the band of stars out there that we call the Milky Way, we're looking towards the center of this great big cluster of stars. If we look the other way, we don't see very many because we're out on the edge of the galaxy. So if we look towards the center of it, we see a lot of stars. If we look the other way, we don't see very many. Okay. Well, the galaxy is rotating, it's moving around, and so our solar system is moving around with it. But notice it takes us about 200 million years to go completely around the center of the galaxy. The center of it is very interesting, of course, because there we're pretty sure there's what we call a black hole, or something I would prefer to call a light trap, because the gravity there is so strong, it is so powerful that even light cannot escape from it. Light emitted from it simply gets drawn back in by the intensely strong gravitational field there. Okay, now that's gravity in the extreme. However, note that we'll be dealing with gravity a lot throughout this course. We'll be dealing with a number of different sciences, physics and chemistry. Okay, we'll be looking at the characteristics of water and the characteristics of the atmosphere. And note that when you look out there at the ocean and you see the surface of the water, and then there's the atmosphere above it, you normally won't see the atmosphere unless there are clouds in it. Okay, but it looks like a pretty sharp boundary. Okay, but it's not. Remember, there's constant interplay between the atmosphere, and the ocean. Just as there's constant interplay between the ocean and the rock floor below it. Okay, so remember, when we think of the ocean as just a lot of water sitting out there, remember it has a lot of interactions with its surroundings, and there's a lot going on inside of it. Well, if we go back then, maybe about 4 billion years ago, and we find that gradually more and more water that was caught up in the formation of the Earth is escaping into the atmosphere. At first it's going to be very, very hot. It's going to be up there in the form of water vapor, in the form of steam, you might say. Okay, but gradually as the Earth cools off, that water is going to come back, and eventually it will accumulate in basins on the surface of the Earth, and we begin to have oceans. Okay. Now, there's still a bit of controversy as to where most of the water came from. Did it come out of the inside of the Earth? We call that outgassing, from gases coming out of the inside. Remember, that's happening today. If you go to a volcano, you'll find that a lot of the gases coming out are simply steam. They're really water vapor coming out. So that's certainly a major source of the water that ended up in the oceans. But also, we have comets coming in from outer space. And sometimes we speak of that as the cosmosphere, the outer surroundings of our planet. There's all kinds of stuff coming in. There's electromagnetic radiation coming in. There are meteorites coming in. There's dust coming in all the time. But one thing that comes in that carries a lot of water with it, is the comet, which is essentially, as some people have called it, kind of a dirty snowball. In other words, there's a lot of water there in the frozen state, but it also contains a lot of rocky, dusty type of material. So we get water from below and we get water from above. Okay, eventually enough of this water accumulated, so we began to have what we call the oceans. Okay, well, taking a look at our planet again, remember when the Earth formed out of what we think originally was a great big cloud of dust, okay, and gases. It contracted, okay, under its own gravity. There goes gravity again. Remember, we'll be hitting gravity throughout the entire course. It got smaller and smaller and denser, okay, and it rotated, and eventually the temperature became so great at the center of this cloud that it ignited a thermonuclear reaction, and we had the sun. Okay, so we think the sun, was formed maybe about 5 billion years ago, and then some of the dust and cloud around the outside of it eventually congealed into the planets. So here we are, Earth. We are the third planet out, and we have Mercury, and then we have Venus, kind of our sister planet, very similar to the Earth in some ways, and then we have Mars. There's a great big gap out there, which is kind of mysterious, and we have the big gas giants further on out, Jupiter, Saturn, Uranus, and Neptune. Well, they're very interesting, and some of their satellites are very interesting. And towards the end of the course, we'll take a look at what's going on out on some of those, because maybe we'll be able to transfer the ideas of oceanography to some of the outlying satellites there. Okay, but that's something that's likely to come sometime in the future. Right now, we're still engaged in trying to find out what we can about our own oceans and our own planet. Okay, so let's take a look at the Earth as it has formed, and I have here a globe. Okay, remember some of the things about the Earth. Because it's relatively close to the sun, originally most of the gases that would have surrounded it essentially would have been driven away by all that heat coming out of the sun. So the atmosphere that we have today, is kind of secondary. It must have occurred later. It must have been formed later than the original formation of the Earth. But remember, from a geographical point of view, we usually divide, what is on our planet into several so-called spheres. Okay, one of them is the geosphere, the rocky part of our planet. Another is the hydrosphere, which is what we're mainly going to be concerned with, the oceans on our planet. Then there's a biosphere, the living things, and then the atmosphere. Okay. Now, since part of the hydrosphere, part of the watery domains of our planet are frozen, we also sometimes call that a cryosphere, a frozen sphere. Think of Antarctica, an entire continent entirely covered by ice. And then the ice that forms on the surface of the ocean in the polar regions, because the temperature drops so low, that the surface of the water, actually freezes. Okay? And then I would also like to add the cosmosphere, okay? Because remember, there's stuff constantly coming in from outer space. Another aspect of that cosmosphere, remember, which is extremely pertinent as far as the oceans are concerned, and something that we'll be looking at in the second part of the course, are the tides. And remember, they are caused by the gravitation, again, the gravitational attraction of the sun and the moon. Well, let's take a look at what the Earth is doing. Remember, it's going around the sun, okay, in an orbit, and we call it an elliptical orbit. Remember, that takes 1 year, okay. As it does that, it's rotating on its axis, okay, an imaginary axle running through, the center of the Earth. That takes 1 day. And remember, those movements are taking place at the same time, like that. Also notice that the Earth is not perpendicular to the plane in which it's going around the sun. It is tilted. It is tilted by 23.5 degrees here. Okay. And that's very important because that remains constant as the Earth goes around. It's always pointing in the same direction. The North Pole always pointing towards a certain star, Polaris, the North Star. Okay. And when you take a look at some of the early voyages, when people first began to learn about the oceans, one of the things is, at least in the northern hemisphere, that was extremely helpful to those early navigators was the fact that they could always look up, at least on a clear day, and see where the North Star was. If it was directly overhead, okay, that meant they would be pretty high, in latitude. If it was right down near the horizon, that means that their latitude would be relatively low. So the stars, remember, the astronomical aspects of what we're going to be looking at have always been extremely important to people who have to travel over the oceans. Okay. Now, notice also that this tilt of the Earth as it goes around, is the cause of the seasons. When you're down at one end of the Earth's orbit with the sun over here, the northern hemisphere is receiving the more direct sunlight. When you get down to the other end of the orbit, it's still tilted in this direction, okay, so the southern hemisphere is receiving most of the light. So that is the southern hemisphere's summer season, okay. Notice the Earth is also at different distances at different times, but that's a relatively minor effect. The main effect that gives us our summer and winter is that tilt, the fact that the Earth is not perpendicular, to the plane in which it's moving, it is tilted. Okay. Well, those are some of the movements of the Earth that are going to be interesting and important to us. Again, it's very important to the ocean, whether it is relatively warm as a result of all that sunlight coming in during the summertime, or relatively cold as a result, of the sunlight coming in at a relatively low angle, which it does during the wintertime. So all of those movements can be extremely important to what goes on in the oceans and, of course, in the Earth in general. Now, looking at our globe again, as we kind of go around from hemisphere to hemisphere, as we'll see, most of the Earth is actually covered by water. Most of it is indeed covered by the oceans. Not only that, but the distribution of the water, is different in the two different hemispheres. Most of the water is in the southern hemisphere. Quite a bit less of it is in the northern hemisphere. So there's a little bit of asymmetry there. Okay. On the other hand, at the South Pole in the southern hemisphere, we have a continent right at the pole, whereas at the North Pole, we have an ocean up there. Okay. Now, what are these oceans? Well, sometimes there's a discussion as to whether we should speak of the ocean or the oceans. We usually divide up the ocean world into 4 different oceans. The biggest one of all, our ocean, right off our coast here, is the Pacific Ocean. Second is the Atlantic Ocean. Third is the Indian Ocean, which is mostly in the southern hemisphere. And finally, the Arctic Ocean, which is relatively small up near the North Pole. However, since they are all interconnected, we can speak also simply of the ocean, of the world ocean. And in fact, that is pretty much our definition of what an ocean or a sea is. If a body of water is a part of that world ocean, if it is connected to it, okay, then we consider it to be, part of our subject, part of, the world ocean, and part of what we call things like sea level and sea surface temperatures and so forth. So, for example, the Mediterranean Sea, okay, it's almost landlocked, but not quite, okay? There's an entrance to it. You can sail right into it, so it's part of the ocean. You can go on even further, up into the Black Sea, again, through a very narrow strait. But again, it's connected to the world ocean, so we consider that to be a part of it also, okay? And again, notice sometimes there's confusion about the words sea and ocean. Sometimes they mean the same thing. When we talk about sea level, we mean the level of the surface of the water, which is really ocean level. We talk about the sea surface also, okay? Again, that's the surface of the ocean, okay? Even in places far inland like the Mediterranean, say, or the Black Sea. Okay. On the other hand, there are some bodies of water that we call seas that really aren't, like the Caspian Sea, which is not connected to the world ocean. It's clear to see why people call it that. It's big, there's a lot of water there, it's salty, okay? But again, it's not, from our point of view, really a sea, because it's not a part of the world ocean. Okay. So these are, again, some things about geography that oceanographers, deal with when we're kind of describing the part of the world that we are especially interested in. Well, the oceans, again, may appear to be just kind of sitting out there, and I'd say, well, there's a big body of water out there, a big pond, a big lake, a big pool of water, and we may think of it as being pretty much inert, that it's not doing much of anything. But note, it is constantly in contact with the atmosphere, and it's constantly being stirred up by the atmosphere. It's constantly in contact with the rocks below, and some of them, as we'll see, are very, very active, so it's being impacted from below. So you might say that the ocean is receiving impulses from above, and from below. Okay, and it's storing up a great deal of energy as a result of this. And of course, we know from the many types of marine disasters that have occurred, just how much energy this can be when it finally comes to shore. Okay, we have to think then of the oceans as not just a great big glob of water sitting out there and not doing anything. Remember, it is extremely active. There's a great deal of energy there, and it's extremely changeable. It's always changing. Think of the El Nino phenomenon, for example, when as a result of a shift in the winds above the ocean, we get very, very large movements of the water itself, which affect very, very large parts of the Pacific Ocean, but also spread out so that it affects different things going on all over the world, what we call teleconnections. In other words, what's happening in the Pacific is felt in all the other of our oceans. Well, again, remember, the biggest of these oceans is the Pacific Ocean. The next largest is the Atlantic Ocean. Also, it's somewhat less deep. The Indian Ocean is third, and it's even less deep. And the Arctic Ocean is relatively small. In fact, some geographers would like to call it a sea because it is much, much smaller than the other oceans. But it has certain oceanic characteristics, so we'll kind of keep it there as one of these oceans, and it is very, very closely connected to the Atlantic Ocean. So it does make sense to consider it to be, an ocean also. Important things to remember here, are all of these interconnections. We see the atmosphere up there, and we see all the water down below. But remember, those gases in the atmosphere are always also being absorbed by the ocean. The ocean has dissolved gases in it, which are constantly being released to the atmosphere. Also, remember, all that solar energy coming down on the surface of the ocean evaporates that water, and that's where the water comes from that feeds our lakes and rivers, on land, for example. So there's a constant interaction taking place there between the oceans and the atmospheres. Also, and this is, of course, something that's very close to us here in Southern California, look at the activity taking place along the shore, where we have waves, which may have been formed thousands of miles out, in the Pacific Ocean, come all the way across, carrying that energy with them, and when they hit the shore, they have a very strong impact, on, the shoreline itself, on the formation of beaches and sea cliffs, and on the life which lives along the shore also. From another point of view, we can think of the oceans as a huge catchment basin for energy, collecting great amounts of energy and eventually discharging it on the shore, the place where it kind of all comes together. This is where the land and the sea, and the atmosphere, and a lot of very interesting types of life all come together. The geosphere, the hydrosphere, the atmosphere and the biosphere all linked together in this extremely active, extremely physically and chemically important area. The fact that we live very close to it and we can get down there and take a look at it, which I strongly encourage you to do, is very, 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 very useful for us to be able to find out actually what's going on our planet. Because this is one of the focal places for the different types of energy which affect what's going on in our entire planet, especially of course in the oceanic world. But again, we can't separate that. We can't separate what's going on in the oceans from what's going on on land. Also, when we think of the winds which are blowing across the ocean, remember, whatever they pick up from the ocean, they're also going to distribute onto the land, and affect what's going on there.